Image F. Assuming same radii and density, opposite-handedness aligned with opposing positive flux would cause significant repulsion unless the strength and phasing of the minor vortices is sufficient. The angle of interaction would be parallel, allowing for the most effective interaction of the minor vortices. Image G. Assuming same radii and density, these two particles may have a strong axis-to-axis bond, but the opposing directions may cause repulsion, and this, combined with opposite-handedness, would cause strong, rapid minor vortex interactions, as they cross over each other at full parallel force. This configuration may also cause an oscillating bond, if any at all. Image H. Assuming same radii and density, this image depicts particles of same-handedness, aligned at opposite axes for strong attraction. The angle of interaction of the flux is in opposition, yet due to the same spin, it may be permanently engaged into a set of minor vortices in addition to the strong axis flow. Both sets of particles are experiencing the same forces as mirror images. Considering the sets as units, they act as two columns of opposite-handedness and mesh together well, with the minor vortices aligned parallel, allowing for maximum engagement. They are only repelled by their free axis both being aligned the same. Thus, only the very ends would have significant repulsion, which may make this form a candidate for long protein chains. Image I. Disregarding density. This model depicts a smaller radius particle engaging a larger one axis to axis. The large amount of flux passing through the smaller particle may greatly increase the force of all of the positive minor vortices, as its energy density would be increased. The distance that the flux of the violet particle went before bonding with the blue particle may now be increased due to the smaller holes. Furthermore, it would be reaching out in different directions. This gives this particle a much greater ability to attract new matter and continue its growth. Image J. Disregarding density. Again, a smaller particle, yet this time its negative axis is bonded to a positive minor vortex of the larger particle. Its spin may be altered by the interplay of the minor vortices of both particles. However, it will be carried to the negative pole of the large particle and possibly end up as image I. Image K. Disregarding density. A smaller particle whose negative minor vortex is attracted to a positive minor vortex of a larger particle. This may cause the smaller particle to spin faster with increased energy density, spraying a spiral out of its major axis. It too will be short-lived as it approaches the major pole of the larger particle, also possibly ending up as image I, or possibly it may become image L. The interaction of the major axes of each particle may repel, keeping the small particle orbiting in the center of the larger. Image L. Disregarding density. This depicts a smaller particle attracted to the positive main axis flux of a larger particle. This may cause the smaller particle to spin faster due to the large influx of energy, spraying out flux from its major axis as it spins. This causes greater distance and area coverage of the violet's system flux, increasing its chances to attract other particles. The interplay of the minor vortices may keep this configuration stable, else it may evolve to image I. Remember, the spray of this flux is actually just the waveform extending due to energy excitation. Image M. Assuming same radius and density, this image depicts two particles attracted by the major poles at 90 degrees. The flux flows from one into another. The minor vortexes are in phase and of sufficient attraction to keep the objects from collapsing into an image H configuration. This configuration works much like the common heliacal gears shown to the right of model M. The angle of 90 degrees shown here is merely an example. It does not intend to bar any other angles. Note that exterior forces can also assist in forcing particles into any of these relationships. It need not be solely self-generated. These simple models have been shown only to illustrate the basic concepts presented in this paper. They are far from detailed. Note also that major axis bonds and multiple energy density levels may be responsible for stronger chemical bonds as opposed to just more shared electrons. Furthermore, electronegativity is a measure of an atom's tendency towards energy density gain, not electron gain. The examples presented so far have been fairly simple. In reality, the interactions would be much more sophisticated. Below are some slightly more complicated arrangements. The more complex a structure gets, the more complex the flux interactions become, and the more characteristics of the specific arrangement manifest. The following examples are of self-similar particles, such as metals. These basic cubic structures will be touched upon. These are, from columns left to right, simple cubic, body-centered cubic, and face-centered cubic, each representing an increase in energy density. A. In a simple cubic cell, each atom has 6 neighbors, is 52% pack efficient, with a void volume of 92.3% of the atom's volume. It takes 8 of these cells in a cube to create the octahedron of sodium chloride. B. The body-centered cubic has an atom between each layer. Thus, each atom has 8 neighbors, is 68% pack efficient, with a void volume of 47.1% of the composing atom's volume. C. Face-centered cubic can be thought of as a dual tetrahedron within a cube. Again, this form proves to be the most symmetrical and dense, with a 74% pack efficiency and a void volume of 35.1% of the composing atom's volume. Image A. These 3 units are locked together axis to axis, sharing the major axis flux in a circuit. The waveforms cycle in on one side and out on the other, like a smoke ring, polarizing the respective sides and creating an overall vortex. Image B. This is a system attracted to the negative side of model A by mechanical attraction, creating a negative center and positive edges on the other side. Image C. Image D. This depicts 2 units of image B united by mechanical attraction. Image E. Adding a positive node, as image B, to this unit would be a building block of hexagonal crystals. Image F. This unit would be a building block of simple cubic crystals. Image G. This unit would be a building block of body-centered cubic crystals. Image H. This unit would be another building block of body-centered cubic crystals. Image I. This unit would be another building block of body-centered cubic crystals. Image J. This unit would be a building block of face-centered cubic crystals. Note, the flux is ejecting out of the page at 60 degrees in this image. Image N. This represents a simple cubic structure. The entire system is at equilibrium. The blue flux lines flow through the entire system, uniting it into one unit, creating a phantom vortex around the substance. The energy spewing from the minor vortices travels little distance before being absorbed again. Very little energy is free from the geometry of the flow lines. The bonds are strong axis to axis, but side to side the flux lines cross. This degree of repulsion, normally held in check by the surrounding forces of attraction, may be overcome by external forces. Such slip planes could be another reason for malleability of metals, and even the liquidity of mercury. For if the angle of Mercury's flux was severe, image 54, and its strength of repulsion near equal to the axis bond, it would tend to shear with little or no force. Image 0. This image shows the simple cubic metal polonium with an interesting feature. It has a cavity. The forces surrounding the cavity would cause any free energy traveling through that area to behave much like the particle of model N in that same location. However, unlike model N, excess free energy can build up in this cavity without affecting the characteristics of the solid. If energy is added to the previous model, the energy density of each individual unit is increased and thus the characteristics of the entire substance changes, possibly manifesting as melting at low levels, or even polonium's high volatility. In short, there is no detention tank for such a flood of excess energy. With a reservoir, as energy is poured into the system, it is processed by the natural mechanics of the system, and energy beyond the processing capabilities would store up in these cavities. However, conducting energy and merely absorbing it are two different functions. Absorbing the energy is transferring the energy into the cavities and the atom itself. To conduct energy would be a function of the efficiency of the atom's ability to take the energy back out of the cavities, and the size of the individual cavities, as a cavity far too big may store energy but may not conduct it. A cavity of a harmonic size in relation to the energy being conducted may conduct it efficiently, such as a resonating cavity. Yet a cavity of a size that causes destructive interference may not conduct at all, regardless of its size. It is thus postulated that the shape of a cavity in a system, in proportionate to the composing atom's size and energy density, may result in higher conductive properties as the cavity acts as a resonant cavity and efficiently transmits energy. If it acts as a powerful resonating cavity, just as a magnetron, it may even emit particles, as polonium does. Such a phantom vortex in a cavity is not rigid and quickly alters its parameters to surrounding stresses. It can bend to transmit energy into minor vortices of surrounding atoms. When the input of energy is withdrawn, it takes time for the energy stored in the cavities to dissipate if they are non-conducting cavities, giving rise to heat storage attributes such as with ceramics. There are basically only three types of cavity, shown below. The tightest packed being the first variety, such as in face-centered cubic and hexagonal closed-packed structures. Right. Even though that face-centered cubic and hexagonal are very similar, there is a critical difference when the cavities are produced. The stacking of face-centered cubic and hexagonal on top and bottom respectively follows the Keller code, white being the first layer and green being the top. The red dots indicate where the floor, gray, can still be seen. On the final green layer of face-centered cubic, the floor can no longer be seen. However, with the hexagonal, there remains a continuous cavity to the floor, separated by tight pyramidal cavities, while the face-centered cubic of the most conductive metals has only one cavity type, which is a concave dual tetrahedron apex to apex.